Okay, this is chapter 16 in our Strength and Materials class, and in this chapter we're going to be learning how to design a beam. Basically, this chapter is just a combination of things we have learned in the past few chapters. We have learned about F sub B, bending stress. So when we design a beam, we need to make sure that the bending stress does not exceed the allowable stress. We've talked about shear stress. So we need to make sure that we choose a beam size that is big enough so that the shear stress does not exceed a maximum allowable limit. And we've talked about deflection. We also need to make sure that our the beam we choose is adequate to provide a minimum amount of deflection, or at least somewhat less than the maximum allowable. So we've got basically three things to check here: bending stress, shear stress, and deflection. Now, this shear stress rarely controls. So essentially what we're going to do with shear stress is we're just going to check it at the end. After we've selected our beam size, we'll do a quick check to make sure that shear stress is not exceeded. In 99 times out of 100, it will not. But it's still a formality we need to attend to. So what we really need to check here is bending stress and deflection. Those are the two major things. And it may be surprising to find out that deflection often controls. So it's very common to select a beam size that is perfectly adequate at resisting stress. It's in no danger of actually failing, but it might deflect too much. It might bounce or sway or just move too much, in which case it would be determined to be unacceptable. So the first type of beam design we're going to look at is steel beam design. So a couple formulas we need to be aware of when it comes to steel beam design is that the allowable moment equals the yield stress times the plastic section modulus divided by some factor of safety. Now, according to the AISC, the factor of safety for beams is 1.67. So this omega sub b is our factor of safety. And in different situations, different structural elements, different materials may have different factors of safety. But when it comes to steel, for steel beams, omega sub b for a steel beam equals 1.67. That's the factor of safety. Zx, if you will recall, we've talked about this in a previous chapter. Zx is the plastic section modulus. That's a characteristic that really only we deal with in steel. When we do timber beam design, we'll be using the elastic section modulus. So plastic section modulus is kind of exclusive to steel. And then, of course, F sub y is the yield stress. Typically, we use wide flange sections. So for a W section, wide flange sections are made of A992 steel, and that particular grade of steel has a yield stress of 50 KSI. So that may not always be the case, but typically, especially if we're using wide flange sections, if the yield stress isn't specifically stated in the problem statement, you can assume that that yield stress is 50 KSI, because this is the most common type of material that wide flange sections are made from. So if we look up here at this equation, this is telling us that the moment is equal to the stress times the section modulus divided by a factor of safety. But typically when we're designing, what we need to do is we need to choose a beam that's big enough. So we want to know, okay, how big does our section modulus need to be? So really we need to rearrange this formula for z sub x. Z sub x is going to equal the maximum moment times the factor of safety divided by the yield stress. So this is our first step in the design process. Is we're going to look at our beam and figure out what is the moment. What is the maximum moment being applied to this beam? This is basically going to be a constant, 1.67, as is the yield stress. It's pretty much a constant as well because the vast majority of wide flange sections are made from A992 steel, which has 50 ksi yield stress. So really it all comes down to the moment. What is the moment? We find the moment, we plug it into this formula, and that gives us the plastic section modulus, Zx. What we're going to want to do then is look in the appendix of our book. There's an appendix that has steel wide flange sections in order according to their plastic section modulus. Let me take a look real quick and see which appendix that is. Okay, I just looked in the book, and it is Appendix I. Appendix I orders wide flange sections by their plastic section modulus Z sub x from greatest to smallest. And so this is what we're going to want to use. Now I'm going to actually drag my ebook over here so you can see. The way this is organized is that see there are these lines here, and what these lines do is they separate the wide flange sections into groups, and within this group, the top number, the bold number within that group, is actually the most efficient within that group. So although, for instance, in this section right here, the plastic section modulus increases from 54.9 to 57 to 64, the weight of the beam does not necessarily increase. It actually decreases 45, 40, 36. And the reason for that is because these beams are getting deeper and deeper. A W10 is only 10 inches deep. A W12 is 12 inches deep. A W16 is 16 inches deep. A deeper or taller beam, a taller cross-section, is going to yield better efficiency. So we actually get a greater plastic section modulus, 64, for a lighter weight of only 36 pounds. Compare that to a W10 by 45. That weighs 45 pounds. That's significantly more weight and actually gives us less in terms of plastic section modulus. So when we solve for a plastic section modulus, if we fall within two of these white lines, we're going to want to go to the top of that group and select the bold section that is most efficient. That's always the goal of the engineer, is to select the most efficient section. So having said that, let's take a look at an example. Example 16.1 is a simply supported beam with a uniformly distributed load. So this is pretty common, the most common support and loading condition. And again, this chapter is basically, in a way, sort of a review of the previous chapters. All we're doing is taking what we've learned previously and putting it all together. So the distributed load here, little w, is 4 kips per foot. The span of the beam is 25 feet. We're given the reaction forces, but we could have found those reaction forces pretty easily. If we have 4 kips per foot spread out over 25 feet, 4 times 25 is 100, and that load is evenly shared by the two supports. So that's 50 kips and 50 kips at the other end as well. So what we need to do, as I said, the first step in designing a steel beam is to find the maximum moment that this beam experiences. We could do that by a shear and moment diagram, but that's kind of inefficient. It's better to go to Appendix H, if possible, and search for the scenario represented by our beam support and loading condition. And since this is the most common type of support and loading condition, it's the number one situation in Appendix H, and the maximum moment is equal to WL, hold on, let me see, what does that mean? WL squared, I just double checked the formula, WL squared over 8. So that's the formula for maximum moment. So our W is 4 kips per foot times the length of 25 feet. Don't forget to square that and then divide it by 8. So the maximum moment that this is going to experience, this beam with its given loading situation, is going to be, okay, that equals 312.5. Let's look at the units here. I've got kips and I've got feet. So that's kip feet. Now, things like plastic section modulus are in inches to the third power. So I'm going to want to convert my feet to inches. So for every 1 foot, there are 12 inches. And so if I take 312.5 times 12, I get 3750 kip inches. So inches are the units I want. That's going to allow me to put that into this equation here. This one right here that tells us that the required plastic section modulus is equal to the moment times the factor of safety divided by the yield stress. So if I come down here, the Zx that I'm going to need for this beam is going to equal 3750 kip inches multiplied by the factor of safety, which is 1.67, and then divided by the yield stress, which is 50 KSI. And so that equals 125.25, and that's in inches to the third. So I'm going to have to refer to the appendix, Appendix I, and look for a wide flange section that will give me a plastic section modulus at least this big. So if I go to the to that part of the appendix, it looks like my best option is a W21 by 62. Now, looking at the appendix, it looks as though a W14 by 74 could have worked. That has a plastic section modulus of 126. 126 is greater than 125.25, but just above that, in bold, is the W21 by 62. It has a plastic section modulus of 144. So it's providing more strength. It has a higher plastic section modulus for less weight. 62 pounds weighs less than 74 pounds. How does it do that? It does that because it's deeper. A deep beam, a tall, deep beam, is always going to be more efficient than a short, stout beam. So the depth is what gives it its efficiency. So it looks like my time limit is nearing its end. So I'm going to pause right here and continue this example problem in the next video.